today's lecture we'll talk about certain implications of the very valuable concept that we talked about earlier, the concept of equivalence. Okay? The first thing that we would like to talk about is, or has to do with one-port circuits. Okay? If you have a one-port circuit, an LTI resistive one-port circuit that contains only LTI resistors, LTI dependent sources, and ideal transformers, then it turns out that that one-port circuit can be represented by a single equivalent component, and that component is an LTI resistor. And now we will try to figure out how that resistance, okay, how the resistance of that equivalent resistor can be calculated. Okay. So here is what we're going to do: a one-port consisting only ideal transformers, LTI resistors, linear time invariant, and linear time invariant dependent sources. There's one detail that we have to be careful about regarding dependent sources. If you have a dependent sources within your one port, its control variable must also be within the one port. Otherwise, we cannot talk about equivalence through a single resistor. Dependent sources whose control variables within the one port is equivalent to a single LTI resistor. Okay. So in pictures, the statement here can be expressed as follows. Suppose that this is your one port, okay? And here, this is how we label the port voltage and port current. Since this is the only pair of wires, this is the only way that this guy communicates with the outside world. By KCL, whatever this current is, this current in that direction, okay, outgoing, must also be equal to R. Okay. So within this box, we have only LTI resistors and LTI dependent sources and ideal transformers. And then here the statement claims that if you have such a circuit, then, and suppose that this is connected to something else, then if you take this thing out and instead connect to that something else, just a single resistor whose resistance you have to compute, okay? Then that thing that this one port is connected to will not feel any difference. That was how we defined equivalence, okay? And that particular resistance through which you can represent this is called input resistance of this one port, okay? And this is the notation that we use to show the input resistance. Okay. If the input resistance of this one port is something such and such, and then this one port is equivalent to this single resistor with resistance R input, I plus minus. Okay. And now In an example, we will see, in a simple example, we will see how one can compute input resistance of a given one port satisfying these conditions. Okay. Consider this one port here with two LTI resistors and one LTI dependent source. And dependent source is independent voltage source 3/2 Ix, and its control variable is this current on that wire. This is 3 ohms and this is 2 ohms. Okay. Since that one port satisfies these conditions here, therefore it must have an input resistance, and now we're going to figure out that input resistance. Okay, what's the corresponding input resistance? Okay, here is the idea, applying which will give us a method to compute input resistance of any one port satisfying the conditions here. Idea is the following: if this one port, let's call it N, A, B, is indeed equivalent to just a single resistor whose resistance is something Rn, AB, then, so that means these 3 bars indicate that, suppose that this thing is connected to something, and then you take that out, take this out, and instead connect this simple single component, that circuit, and that circuit will not feel any difference. Or equivalently, suppose that you go to lab, you have this one port and it's equivalent. So no matter what voltage and current tests you apply at the port terminals, you will always get identical results for both of those components. Okay. So that means if you connect the current source here and same current source there, then the voltage that current source generates here and here must be the same. And that's the very particular situation that we will use to compute the input resistance. Okay. Okay, but before that, let's make our idea clear. If this thing is equivalent to that resistor, then we must have V configuration 1 equal to V configuration 2. The voltage in configuration 1 and voltage in configuration 2 must be the same. Where by configuration 1 and configuration 2 we need the following. For the following. Okay. Now, this is the case 1 or the circuit 1 or the configuration 1. This is A, this is B, and here we have this is A, this is B, and here we have R in. Now what we do in the lab, suppose that we have this component and this simple resistor. To both one ports we connect the same input or same source. Let it be just 1 amp current source. Okay, 1 amp. Okay. Connect the same current source. Now this current will generate a voltage at the port terminals. Likewise, this current will generate a voltage across the terminals A and B. And if those two things are equivalent, those two voltages, which we're labeling plus minus V sub 1 plus minus V sub 2, those voltages must be the same. Okay. And now, the relation of this voltage to that resistance is obvious. Rin equals V over 1. This resistance, by Ohm's law, must equal the voltage across its terminals divided by the current passing through it. By KCL, the current passing through it is 1 amp. The voltage across its terminals is V2. Therefore, V2 divided by 1, which is V2, must be Rin. Okay. And this V2 equals V1 because of that equivalence. And this simple set of or chain of equalities is what we're using to compute Rin. Note that Rin is something that we want to figure out. It's unknown initially. Okay. And then, since it equals V1, and V1 is the voltage here, and we assume that we know what's inside this one port. Therefore, we can solve this circuit. Solving this circuit will give us this voltage. Therefore, V1 is known or can be computed. Can be computed by solving circuit in configuration 1. Okay, and once you solve for that voltage gives you in ohms the input resistance that you're looking for. So let's therefore return to our example. Okay, so this is what we're trying to figure out. Where is the solution? Let's connect a test source of 1 amp. Okay. And then what we're trying to figure out is this voltage. If you can find this voltage, that voltage will directly give us the input resistance of that one. Okay. So let's call that voltage plus minus V1. Okay. Now we have methods that we can use to solve LTI circuits, node voltage method and mesh count method. So let's apply node voltage method. Let's choose a ground node. So let that be our ground node. And then there remains only just a single node, and let the node voltage for that node be E1. Okay. So let's write KCL at this node. This current plus this current plus that current must equal to 0. Okay, so we have E1 minus this node voltage, which is 3 over 2 Ix divided by the resistance in between. Okay, that's this current. And then we have this current plus E1 over 2. And finally we have this current, which is minus 1 amp. And that must equal 0. Now that equation contains two unknowns. So we have to figure out Ix in terms of known voltage, the formulation variable. But we don't even have to do that. We can directly see what Ix is in this simple circuit. By KCL, if this is 1 amp, this Ix must be minus 1 amp. Okay. So Ix equals -1. And so replace Ix with -1, and that gives you E1 plus 1.5 over 3 plus E1 over 2 minus 1 equals 0. Okay, a single equation only in terms of E1, and that gives us E1 equals 3 over 5 volts. If that's E1, then V1, this voltage, is no other than that node voltage E1. Therefore, V1 is also 3 over 5 volts. And then finally, input resistance is this voltage divided by this current. Okay? V1 over 1 gives us 3 over 5 or 0.6 ohms. Hence, the input resistance equals 3 over 5 ohms. Okay. Now we will extend this notion of equivalence. Note that now we're talking about, so far we've talked about one port or two terminal circuits when we use the word equivalence, but that can be extended to let's say 3 terminals or even more. But we're gonna talk about the 3 terminal case for a while, because it's quite important, especially for the 3-phase circuits when you will eventually see in 202. So our next topic, therefore, is a special type of equivalence between 2 special 3-terminal components. Okay. So delta Y transform. Okay, suppose the following 3 terminal components are equal, meaning that no matter what current and voltage tests you perform at the terminals, you always get identical results. And one circuit has this topology. Okay, this is called the delta connection, and the other has this topology. Okay, which is called the Y. Well, this looks like an upside down Y, but nevertheless it's called a Y topology or Y connection. Now let's do the labeling. Let's be careful about labeling. Suppose that we're labeling these nodes as A, B, and C. Okay, A, B, and C. And here we have the resistance across the corner A is called RA, this is called RB, and this is called RC, and so on. Okay. Then here we have also 3 LTI resistors, the resistances, let us call R1, R2, and R3. Okay. And then we're told that this circuit, let's say, and this circuit are equivalent to one another. Okay. So this is in a box, let's say, this is also in a box, and from that box, 3 wires, or from those 2 boxes, 3 wires are sticking out. And all those wires are labeled ABC here and also ABC there. So no matter what voltage and current tests that you apply from those to those terminals, you always get identical results here and there. Okay, that's what we mean by equivalence of those 2 circuits. Now the question is, if this is equivalent to that, clearly there must be some relation between this set of resistances here, RA, RB, RC, and this set of resistances here, R1, R2, R3. And now what we will try to do is we will try to discover that relation between this set of resistors and that set of resistances. Okay. So that's the problem that we will try to solve. Find the transformation relations between the triples RA, RB, RC, and R1, R2, R3. Okay, and here is the idea. If these two things are identical, if I measure input resistance seen from the terminals A and B here, it must be same input resistance measured from terminals A and B in the second circuit. Okay, so if I apply all those constraints for all pairs of terminals here and here, I get enough many equations to find the transformations that we're looking for. So that's what we're going to do now. Let me write down the idea. Here is equate the equivalent input resistances. Okay, C the pair of terminals AB, BC, and finally CA. Okay, so what we mean by that is the following. R, A, B. So I'm measuring, let's say, the resistance C from the pair of terminals A, B here. So I connect my ohm meter to those pair of terminals, and while doing that, I do not connect anything to this terminal C. Okay, and I read something, let's say 17 ohms. If this is equivalent, and if I do the same procedure here, connect an ohm meter between the terminals A and B, and while doing the measurement, I do not connect anything. This terminal, that's open, okay, it's unconnected anything. I should measure the same thing that I measured here, let's say 17 ohms, okay. Likewise, if I do the same thing to remaining pairs of terminals, I should always read the same number here and here, okay. And that sameness will give us the answer. Namely the transformation that we're looking for. Now, RAB, what's the resistance read from a pair of terminals A and B? So we have here RC. Since nothing is connected to C, this resistor and this resistor, they are in series, so that's RA plus RB. Therefore, what we have, the overall resistance is RC in parallel with RB plus RA. Okay. So RC parallel with RA plus RB. Okay. And that's, you can use the formula RA plus RB. When we have two resistors in parallel, the equivalent resistance is the product divided by the sum. The product is RC times RA plus RB over the sum is RA plus RB plus RC. Okay. So that's what I read for this guy. And if I do the same procedure here, but the input resistance seen from the terminals A and B is R1 plus R2. Since nothing is connected to the terminal C while making the measurement, this R3 has no effect whatsoever. In other words, R1 and R2 in that case become in series because there is no current escaping to R3. It's the same current traveling through R1 and R2. R1 and R2 become series, therefore the equivalent resistance is R1 plus R2. Okay. Since RAB here and RAB here must be the same because of this equivalence. Okay, this must also equal to R1 plus R2. So that's the first equation that relates this set R1, R2, R3 to set RA, RB, RC. Okay, so let's call this equation 1. And then let's do the same thing to other pairs of terminals. RBC is equivalent resistance C from this pair of terminals is RA in parallel with RB, RC. So that's RA, RB, RC over RA plus RB plus RC. And that equals what I read from here, which is R2 plus R3. That's our equation 2. And finally, R CA equals RB, R C plus RA over RA plus RB plus RC. And that must equal R1 plus R3. Equation 3. Okay. Now here, let's introduce a little bit of a trick, so that from that trick we can figure out the relation between the sets, the triples. So first, let's sum all those three equations. Okay, equation 1, equation 2, and equation 3. So that equals on the left-hand side, we have 2 times RA, RB plus RB, RC plus RC, RA. Note that the denominators are the same. So all those guys are A plus RB plus RC. And on the right hand side we have 2R1, 2R2 and 2R3. Okay, so 2 times R1 plus R2 plus R3. Okay, these 2's nicely cancel. That gives us our equation number 4. And then using equation 4 and the first 3 equations, we will now easily obtain what we're looking for. Okay, so now let's subtract equation 2 from equation 4. Okay, this is equation 4 and this is equation 2. The right hand side here we have R2 plus R3. Here in the right hand side we have R1 plus R2 plus R3. So if you subtract 2 from 4, R2 plus R3 will just disappear, and what you're left with will be R1. So that gives us R1 equals, therefore, this minus this thing. And this thing this thing has RA, RB and RA, RC. And then this term and that term, they disappear therefore. So what we're left with is RB, RC on the numerator, and denominator is the sum of 3 resistances. So what we have therefore is R1 equals RB, RC over RA plus RB plus RC. Okay. Likewise, 4 minus 3 will give us R2 equals RA, RC over RA plus RB plus RC. And 4 minus 1 gives us R3 equals RA, RB over RA plus RB plus RC. Okay, so if you have the delta connection, that means if you know RA, RB and RC already, then from that connection you can go to the Y connection through these relations. That is, from RA, RB, RC you can use these relations to compute R1, R2 and R3. Okay, now let's also figure out the reverse relation. That is, if you know the Y connection, how to move on to the delta connection. Okay, so that's the second part. Now, okay. Okay. Now we write R1, R2 plus R2, R3 plus R3, R1. Okay, here we have R1, R2 and R3, and then using these equalities, we're now writing that R1, R2, R2, R3, and R3, R1. Okay, and that gives us the following ratio: RA, RB, RC times RA plus RB plus RC, and here we have RA plus RB plus RC squared. Okay. And then one of these guys will cancel with that, and we have that relation. Okay. Now this equals what? Okay, let me rewrite it in a clean way. RA, RB, RC over RA plus RB plus RC. Okay, so this ratio equals this sum of products. Okay, now note that, for instance, R1 is here. Okay, RB, RC over RA plus RB plus RC. Therefore, this thing equals RA, R1. Likewise, it equals RB, R2, okay, or RC, R3. Okay. Everything we need is in this equations that we just derived. Okay. Hence, if this thing equals RA times R1, we can simply divide this by R1, and that gives us RA. Therefore, RA equals R1, R2 plus R2, R3 plus R3, R1 over R1. And RB equals the same numerator divided by R2 and so on. R1, R2 plus R2, R3 plus R3, R1 over R2. And finally, RC equals R1, R2 plus R2, R3 plus R3, R1 over R3. Okay. Now this is the set which allows you to go from delta to Y, and now this is the set that allows you to go from Y connection to delta connection. Okay. Now an important remark is, okay, let me write it here. If if you have the following symmetry for the delta over Y connection, then the remaining connection is also symmetric, and the relation relation between the corresponding resistances is as follows. If you have this supersymmetric delta connection, that is all the resistances are equal to one another, then this is equivalent to a symmetric Y connection. So all these resistance values are equal to one another, and furthermore they equal to 1/3 of the individual resistances here, R over 3, R over 3, and R over 3. This relation will be quite useful in 202 when we study balanced three-phase circuits. Okay. Okay, now let's use one set of relations that we figured out to solve for an example. Okay. Here is an example. Let me squeeze it here. Suppose that we have the following one port that consists entirely of LTI resistors. And here we have 7 ohms, 20 ohms, 10 ohms, 50 ohms, and 40 ohms. Okay. Now what we're asked is the input resistance, okay, for that one port. Okay. So here is the way to solve it. Of course, we can apply our test source method, that is, connect here, for instance, a 1N test source, and by applying mesh analysis or node analysis or something else, you can solve for the voltage that appears across the terminals of that current source. And that voltage gives us, in ohms, the number that we're looking for, the resistance. But here's another way. Let's use our latest discovery to solve for the input resistance using delta Y transformation. Okay. So here is a way to solve it. Now, let's concentrate on one of the delta connections. Not that here we have a delta connection, here we have another delta connection. Let's consider the one at the bottom. Okay. So we have RC equals 10 ohm, RB equals 50 ohm, and RA equals 40 ohm. Okay, so we're concentrating on the delta connection that appears here, and we're labeling the nodes as follows. This is node A, this is node B, and this is node C. We know that. Since we know that this can be represented by a Y-connected 3 resistors, okay? And then that means, because of the very definition of equivalence, we can take this thing out and connect that Y-connected set of resistors, and this thing will not feel any difference from the outside pair of terminals, okay? So let's do that. That's what we want to do. Because after Y connection, once we replace this by a Y-connected circuit, everything becomes either series or parallel, and then by just a very simple series of computations, we can quickly reach the ends. Okay. Now this is equivalent to connected set of resistors. Okay. A, B, and C. Let's call this. This is R1, this is R2, and this is R3. Okay. And we discovered the transformation from the set RA, RB, RC to the set R1, R2, R3. So let's quickly compute R1, R2, and R3. R1 equals RB, RC over RA plus RB plus RC. Okay. RB, RC gives us 500. Okay. 50 times 10, 500. RA plus RB plus RC gives us 50, 40, 10, 100. Therefore, R1 must be 5 ohms. Likewise, R2 equals RA, RC over RA plus RB plus RC. Okay. RA, RC, 10 times 40 is 400. Divided by the same denominator, 100. So therefore, R2 must be 4 ohms. And finally, R3 is RA, RB over RA plus RB plus RC. RAB is 50 times 40. That makes 2000. Over 100 gives us 20 ohms. Now we know all the resistances in the Y connection. Hence we can take this guy out and plug in the Y connected circuit or sub-circuit, and then using the new connection we must be able to easily compute the input resistance. Then we have this was A, this was B, and we had C. $70 ohm, 20 ohm, 10 ohms, 50 ohms, and 40 ohms, and this is we're calling C. Okay. Now this is equivalent to now A, B, C, this delta connection, we're going to replace with that Y connection. Okay. A, B, and C. So here, this must be R1, and R1 is 5 ohms. This must be R2, and R2 is 4 ohms, and this last guy is R3, and it's computed to be 20 ohms. Okay. Now this is equivalent to what? 7, 5. Okay. This is Rin, and Rin equals what? So we have 7 and 5, 12. Okay, this is 12 ohms. 20 and 4, this is 24 ohms. This 12 ohm and 24 ohms, they are connected in parallel. 12 parallel 24, and which gives us 8 ohms. And that 8 ohm is in series connection to 20 ohms. So that's 20 and the overall result therefore is 8 plus 20, 28 ohms. Okay, so that's a neat example where you can apply delta Y transformation to reach the answer in a straightforward manner.